Tu me dis quand c'est bon. Ah, c'est bon? Okay, so Olivier, Martin, Georg, now we change something. You should be able to mute and unmute when you want. Can you check?
Yes, it works.
Yeah, it works.
Wonderful.
Okay, thank you very much. Donc, on n'attend plus que Edouard. Bon, il arrive.
Ah, ça va. Peut-être fermer la porte après.
Tout le monde est bon.
Bon, alors on va y aller. Donc, bonjour à tous et merci à ceux qui sont là par Zoom. Je sais pas quoi. Thomas, vous avez une quarantaine de minutes pour présenter votre thèse.
So hello, and thank you everyone for being here or online. And thank you for attending my PhD defense on language as a cognitive tool for open-ended agents. So in the past decades, incredible advancements of artificial intelligence have been made in several domains, such as visual recognition or playing games like chess, Go, or StarCraft, and even beating human master in these different games. However, this progress has been made in specific environments with well-defined problems. And we are aiming to undo artificial intelligence agents with human-like intelligence, and they are able to continuously improve by themselves and explore the environment. So to study the interaction between an agent and its environment, we are placing ourselves in the reinforcement learning framework. So in this framework, so here, for the sake of the example, we are taking a maze. And the agent observes its a state, so its position inside the maze, and then generates an action. For instance, here, move it. And the agent returns a new state that can be observed by the agent. So its position, a different position inside the maze, and the reward that is 0 until the maze is finished when it's turned to 1. And the goal in the reinforcement learning framework is to maximize the discounted sum of reward. And the discount factor here mean that a future reward is less preferable to one that we get right now. Usually, in classical reinforcement learning environments, agents face constrained dynamics and get predefined goals with predefined reward that have been tuned to these specific goals. So for instance, in Gym Minigrid, the agent has to reach this green cube, or in New Joko, moving this 4-leg spider, or here, moving a robotic arm is in MetaWord. So it's always specific goals already specified with reward that have been tuned for these goals. However, when an agent faces a natural environment, our environment, it contains rich and complex dynamics, and there is no clear objective. Crucially, there is no clear objective. So in such environment, we need open-ended process. And in this process, endow the agent with the ability to explore the environment and continuously discover new artifacts and learn new skills. So a way to do that is first like a better exploration of the environment by intrinsically motivated agents, meaning agents that are able to generate their own reward, that give the reward to themselves, so an intrinsic reward, by opposition to an extrinsic reward, that is the reward given by the environment. And such a reward should encourage the agent to discover the environment, to explore the state space, and discover new unseen transitions. An excellent example of such an application of such a method is the one from the paper from Belmare and collaborators, in which an agent has to solve the game Montezuma, which required an extensive exploration of the environment to solve it. And the agent received an intrinsic reward that is equal to the inverse squared root of the number of times a state has been visited. So more time an agent spend in the same state, less reward you receive. So that should push him to discover new states and explore more the environment. And that's what we can see when we applied such a bonus. However, being able to explore the environment is not sufficient for an open-ended process. The agent should be also able to explore the goal space. And the agent should be able to invent, select, and solve its own goals. In a word, it should be autotelic. So in this framework, the agent generates its own goal and get a reward that is correlated to this goal. So we want an agent that is able to select its own goal, but how? Empirical studies have shown that humans tend to select goals on which the evolution of their competency is maximal. So the interestingness of a goal is proportional to the learning progress on this goal. And so the learning progress being the evolution of the competence. So here the humans tend to select the goal 3, then 2, on which they are progressing the most first, and never select the goal 1 or 4 because they are either too easy or too difficult to make any meaningful progress. So an excellent application of the usage of learning progress for autotelic selection of goals is the work from Forestier and collaborators, in which a robot, a blue robot here, can control a contraption through its arms. So it can move its arms and move a joysticks that move a little robotic toy, and the robotic toy can move a ball, and the ball rolling generates some sounds, and there is also some lights, and there is a distractor, a little robot that is not controlled by the joysticks. And in this complex and continuous environment, the selections of goal using learning progress allow the agent to first learn to control the arm, then the joystick, then moving the robots. So it allows the agent to learn to use objects as tools. However, in this setup, there were limited generalization possible, and the goal space was relatively small. And how can we have a large and diverse goal space? We need some ability to generalize, because an agent confronted to the natural goal space, we face thousands of goals, millions of goals, and it needs to have a method to face such a rich goal space. And language can represent goals in an open-ended manner, because it allows agents to evolve in complex environments through categorization and generalization. For instance, for human, all of these vehicles can be called car, even if there are various shapes and colors. And we can use some generalistic sentence, such as she can drive a car, and it's applied for all of them. It also be shown by Hill and collaborators that specifying goal in natural language for an artificial agent help the agent to generalize more. So for instance, here, the agent was trained on collect green square and collect red circle, and was easily able to generalize to collect green circle. Another interesting property of language is the compositional nature of language. And thanks to this property, that can be leveraged to generate creative goals. So language can help to represent a rich and diverse goal space. And interesting use of the compositional nature of language is the work from Cedric Collard and collaborators in Imagine, in which an agent is coupled with a social peer that describes the different goals it has reached as he explores the environment. So for instance, here you grasp red water, or the goal growing blue lion. And then the agent tries to automatically select the goal and train on them, so grasping red water or growing blue lion, but also leverage the compositional nature of language to create new, never seen goal before, such as grow red tree. So it's a way to leverage the properties of language to create new, diverse goals. However, in this work, they use a very simple grammar with limited and templated formulations. And we want to have more natural expressiveness and to reach a more diverse kind of goal. How can we do that? So in recent years, large language models have appeared as strong statistical model of natural language. They have been trained on millions of texts, and from that they are able to embed general knowledge about our world. So for instance, the affordance of objects. If we ask an LLM, where is the milk inside the kitchen, it would probably say in the fridge. And LLM can also leverage the diversity of natural language and so are able of linguistic creativity. So LLM can help. That's a small summary. Here, we want an agent that is able to explore both its environment, but also the goal space. And LLM, thanks to its knowledge about the world, can leverage them to plan and to efficiently explore the environment. And they can also generalize between goals inside the goal space. They can also be used to explore the goal space, as they can understand non-completed goal, and they can leverage the properties of language to generate new interesting goals. So that's why I get interested in this thesis in LLMs as autotelic RL agents. And I directed my research through 3 questions. The first one is how to internalize the rules of the environment. And I developed that through a work called GLAM that I will develop later, in which we ground LLMs as RL agents inside an environment. Another work is called Word LLM, in which we internalize the environment rules and discover the environment rules. A second question is how to explore the goal space. And I studied this question first in the work called Magellan, in which we use an LLM to estimate the learning progress of the agents and also generalize this estimation. And another work is autotelic LLM, in which the LLM are used to do some goal generation. Finally, the last question is how to efficiently learn new skills. We developed this question in hierarchical, where I use hierarchical framework coupled with a LLM to efficiently learn new skills. Another work that I did is exploiting linguistic abstraction in Eager to foster the learning, the efficient learning of skills. So in the first part, I want to explore how we build an LLM RL agent in GLAM. It's a work that I did in collaboration with Clément Romac and Thomas Wolf, in addition to my supervisors, Sylvain Lamprier, Olivier Sigaud, and Pierre Vaudeillet. And before using an LLM as an RL agent, it's interesting to know how an LLM is trained. So an LLM is a statistical model of language that is trained to predict the next token. And the token is just a segmentation of a text. And they are trained on billions of tokens that are scrapped from the web. So here, the LLM is trained to predict the word morning, knowing the word this, and then predict the word I, knowing this morning. And crucially, such models have no abilities to intervene in the word. They just predict the next word, knowing the previous one. And though they cannot learn from data that they are collecting by interacting with the word. We're saying that the LLMs are not grounded. But what are we meaning by grounding? The most well-known form of grounding is direct grounding. It's when we link a perceptual modality, for instance, the image of this chair, to a symbol. For instance, here, the word chair. Another form of grounding is grounding transfer, where we link an abstract concept, for instance, the concept of justice, with a symbol, the word justice. Is usually done through distributional semantics, where we look at the relation between the different words to understand some meaning, to get some meanings. And finally, the functional grounding. It's the type of grounding we're interested in here. It's how you can use symbol to model, predict, and control external physical processes to solve a goal. So here an example is you have a description of a scene where you see a red ball 2 steps forward, you see a blue box 1 step left and 4 steps forward, and you move 1 step forward. What you see is every element are moved 1 step closer to you. So you see now the red ball 1 step forward. So, so that's the functional grounding. And LLM, as I explained before, their weakness is that they are not grounded. Several prominent AI researchers, among which Yann Lequin, have stated that language model needs sensory grounding for meaning and understanding. And thus, following their advice, we have presented GLAM, that is the first method to ground LLMs by making them interact with an environment. So a short overview of GLAM. We have an LLM that now acts as the agent's policy. that interact with the textual environment. And this textual environment here is called baby AI text. We have made it from the one called baby AI. And what is interesting about this environment is first, it contains partial observations, and then it has spatial properties, so that are not usually present in the text on which the LLM have been trained on the web. And finally, there is a large diversity of goals. So the textual environment generates a description of the scene. So here the little image is not passed to the LLM, it's just for us to visualize. And then the LLM generates an actions that will be acted out in the environment. So GLAM step by step. So we have the baby AI text that will generate first a goal and an observation here. The goal and the observation will be concatenated to generate a prompt that is passed to the LLM. And the LLM will use this prompt to run different actions among the possible ones. And from this distribution over the action space, we'll select specific actions and we'll update the LLM using a classical error algorithm called PPO. Thus, the question is how we can use an LLM to measure the probability of an action. So here, what we did is just doing the ratio between the log probability generated by the LLM about, for instance, the action go forward, normalized by the sum of probability of the log probabilities for all the different actions possible in the environment. And we get the log probability of one action, for instance, go forward, using the chain rule. So by decomposing, for instance, go forward, the log probability of go forward is equal to the log probability of go knowing the prompt, added to the log probability of forward knowing the prompt and go. So it's how we get the probabilities from the LLM to select the actions. And we tested our method in the baby AI text environment that contained 5 kinds of goals. The first one is go to object. The second one is pick up an object. The third one is put an object next to another object. The fourth one is pick up an object, then go to another object. And finally, unlock a door that contains the fact that you need to get the key, the correct key before. In this environment, you have one room, you have 6 possible actions, and you have 8 distractors. And the prompt that is passed to the LLM is the concatenation between the goal and the past observation and actions. So we observe the average success rate, the evolution of average success rate of our method that is called here gflantify because it's GLAM applied to a pre-trained Flantify LLM. And we compare it to 3 baselines. So NPAE, that is the same setup that GLAM gflantify, but with randomly initialized weight, is just to see if the results here are due to the size of the network. We compare it to DRRN, that is a state-of-the-art ARL method in textual environments. And we pass to it the same prompt as the LLM in gflantify. And finally, we compare it to symbolic PPO. It's a bit different because it's used symbolic observation instead of text. So that should be used an indication because it's not taken the same observation. But this observation, in a sense, would make the task easier because it's already contains some geometrical properties inside the image. However, our method outperforms all the baselines. And we can see that the GLAM method is able to ground the agent more efficiently than the other method inside the environment. And the LLM quickly finds strategies. So what is very important is to verify that our method allows for true grounding of the LLM inside the environment. So does it has learned the geometrical property of this environment through the interaction? A way to verify that is to replace the elements inside this environment, but elements that have never been seen. For instance, here we replace a box by a car, a ball by a table. And if the LLM is truly grounded, it will not be there will be no loss in the success rate of the agent because if you tell it go to X and X is described 3 steps forward, you just have to move forward. And what we can see is there is the results are almost the same. And even if we replace word by word that does not exist, an adjective that does not exist, we still maintain excellent results, showing that the LLM, through its interaction, is truly able to be grounded inside the environment. However, when we test it on the generalization and new tasks, either by the composition of 2 previously seen tasks or by changing actions by synonym actions, we see a strong degradation of performances. And in the paper, we interpreted that at that time as the fact that the LLM kind of overfits on, because it was trained on just a few tokens for thousands of interactions. And so in our paper, we thought it was due to overfitting. And we pushed that further in another paper on which I collaborated with Salim IC. In this paper, we've shown that LLM RL agents tend to overfit on the prompt, meaning that if they are trained on this prompt P0, that is the one that we use in GLAM, they tend to be bad on the prompt P2, for instance, here using HTML balise. And that's an issue. And to mitigate this prompt overfitting, we propose to add a contrastive loss in addition to the PPO loss that force the LLM to create the similar kind of representation for the same state through different prompts. So here, before the contrastive loss, we see that the states are clustered depending on the prompt that is used. And now the states are clustered because there are different states. Thus, in conclusion, we have trained an LLM as an RL agent, and we have shown that through this interaction, it is functionally grounded in the environment. And thus, we get an efficient method to explore the environment that is able to generalize between goals. However, the exploration of the environment is not the only thing necessary for an open-ended agent. It also needs to explore the goal space. And here, the goal space is of a limited size, and the goals, crucially, are uniformly sampled. And they are not adapted, thus they are not adapted to the level of the agent. You can see that here, at the end of the training, G25, master, go to, and pick up, but they are sampled as much as the other goals. So there should be a more clever method to select goals that are adapted to the level of the agent. And we tackle this question in the work called Magellan, in which we explore the goal space. It's a work that I did in collaboration with Loris Gavin and Clément Romac and Cédric Collat, in addition to my supervisors. In this work, we use an LLM to estimate the learning progress and to generalize it over a goal space, and use that to build an automatic curriculum. So as we have seen before, using learning progress to choose automatically the most suitable goal is a good option. And learning progress here is defined as the derivative of the competency over time. And from now to the end of this presentation, we say the competency is the success rate of the agent over a goal. And usually we approximate this derivative by just doing the difference of competency at time t and at time t minus n, so with a sliding window. An open-ended agent tends to face a large and evolving goal space. Evolving because as it explores the environment, it will discover new goals and try to reach new goals. So it's a characteristic of open-ended agents is to face this growing and large goal space. And selecting in such a goal space region with high LP is very difficult because you can have few goals with high LP and most of the goals with very low LP, learning progress. Empirically, a way to measure, to calculate the LP is just first to do some rollouts on all the goals present in the environment, and such that we get a knowledge of the competency on all the goals and then deduce the LP. However, if you have thousands and millions of goals, it's absolutely untractable, extremely costly, even if it's highly accurate. So an idea is that the current competence can be approximate from past experiences. And you have a buffer in which you keep all the success and failures, represented here by 0 and 1. And you get that for all the goals you have practiced, you have sampled. And when you need to recover the learning progress, you just cut the buffers into half. In the first half, the older half is just to represent the competency at t minus n, and the second half, the competency, you get the competency at t. However, this method tends to be kind of sparse in terms of data. First, partially because you can have sampled just a part of the goal space and missing some information for the rest of the goal space, and also temporarily because some goals that have been sampled a long time ago, now that their information can be kind of irrelevant for having an accurate estimation of the competence. And finally, if you have it, you can use expert knowledge to group goals together depending on different categories. And you just need to sample 1 or 2 goals inside each categories to have an idea of how the competency of the category progress and then deduce the learning progress. However, even if it's computationally efficient, that require external knowledge that we cannot have when we are doing open-endedness. So empirical evaluation of learning progress in large goal space is very challenging. Learning progress is too costly. Online learning progress tend to be not accurate in large goal space, and expert knowledge required external knowledge. And we have seen in the previous part that LLM RL agents are able to generalize between similar goals, and thus we will need a method that is able to generalize this learning progress estimation. So in Magellan, the idea is if we're in a linguistic goal space, we can leverage linguistic clues to generalize the learning progress beyond the observed goals. So here, a quick overview of the mechanism. So we have a large and evolving goal space G, where in Magellan, there is first an LLM RL agent, as described before, that interact with the environment. And because we are inside the metacognitive framework, the LLM is also used to estimate the competency over the goal space at time t and at time t minus n. And from that, we can recover the learning progress over the goal space. We pass that to a goal selector, and then we can automatically sample goals inside the goal space. So then the LLM RL agent is able to build its own curriculum. So how we did that in practice? On a textual goal GE, we train an LLM to predict the competency using the past attempts of the agents, and we store the weight inside a buffer. And then when we want to estimate the learning progress on this goal GE, we use the weights to calculate the competency that we have estimated at t minus n on this goal G, and we do the same for the goal at time t. And then we can recover the learning progress by doing the difference between these two competency estimation. Thus, because we are using an LLM, we can hope that it is able to generalize from one kind of goal to another kind of goal, leveraging linguistic clues, and that they can be used on very large goal spaces. We test our method in the little zoo environments, in which the agents can combine different elements to get new elements. For instance, here you can combine water and seeds to get plants. You can put a plant and a baby herbivore to get a big herbivore, and this big herbivore you can feed it to a baby carnivore and you get a large carnivore, an adult carnivore. At the beginning, you have at each turn you have a setup with different elements from the different categories explained before, and the agent has to choose a goal to make its competency maximally progress, and then you will try to reach this goal. The catch here, the difficulty, if there are a lot of impossible goals. Indeed, if you try to grow a carnivore but you lacking a seed, you will never grow a carnivore. It's impossible. And thus, it's not trivial to know when a goal is impossible. The goal you can reach here is impossible, because you need to understand the underlying dynamics of the environment to decide if a goal is impossible or not. And it's very important, because if you are not finding which goals are impossible, you are losing some impossible goals, and you're losing time. And then you have a different kind of goals, such as grass, grow plant, or grow herbivore. And you see that due to this structure, the grow carnivore are very sparse, and you have almost none of them. And as you have none of them, it's very difficult, and you need to have a curriculum very precise to be able to reach them. So we compare our method to other baselines, such as a uniform or online ILP. So the uniform, you just select all the goals randomly inside the goal space. The online ILP baseline, you're keeping an archive in which you track the competency over the different goals inside the goal space. And finally, the expert knowledge online ILP use expert knowledge to group information. However, it's an upper bound, because usually in open-ended framework, you cannot have access to this expert knowledge. And what we can see is our method, except from the expert knowledge one, is the only one that is able to recover the growing carnivore part of the goal space. That is able, to learn this part of the goal space. And we have a very similar dynamic to expert knowledge online ILP method. So being able to learn inside a large goal space is very important, but as I said before, open-ended agents tend to learn inside evolving goal space. And how can we test that? We did that in the experiment by training an agent during 150,000 episodes, and then we stop the training, and we remove all the goals previously seen and replace by new goals that have never been seen before, but that are from the same categories. For instance, we can have trained on grow a cow, and then we remove it and replace it by grow a giraffe. And because it's from the same category, you should be able to recover its competency on it. And we can see that our method, so Magellan, has a similar dynamic as the one that uses expert knowledge, that already know which group a goal is in, and we are more efficient than online ID, crucially, that need to resample goals inside this new goal space to be able to correctly select the new goals. So Magellan is able to generalize over a large goal space. Finally, if we are looking at the embedding space at the end of the training, we can see that the embedding space that have been learned contain two kinds of information. The first kind of information is a semantic information. So the goal, such as grass goal, or grow plants, or grow carnivore, are clustered differently. And a second kind of information is the competency information. The goals that are possible here and the impossible goal here. And what we can say is we can also see that the test and the train are correctly positioned inside the embedding space. So in conclusion, we have used an LLM to estimate learning progress, and we are also able to generalize to unseen goal. And this method functions in very large and evolving goal space, allowing for an agent to generate its own curriculum. However, being able to choose correctly a goal inside a goal space is not sufficient. You also need to be able to learn efficiently. Indeed, because if you select a goal because if after some time you select more and more complex goal, at some point you will take so much time to learn a skill that your progress will kind of stall. So that's a question we tackled in this paper called Heraclis that I did in collaboration with Loris Gavin and Clément Remac, and in addition to my supervisors. And in this goal space, humans usually acquire remarkably diverse repertoire of skills continuously throughout their lives. So from learning to walk to learning to play the guitar or chess or doing some science. And the progress in artificial agents and the opposite can kind of stall at some time if the trajectories become too long and too complex that can block the progress. So learning efficiently and an increasingly large set of skills is a true challenge. Usually, when we want to learn efficiently, we place ourselves in a hierarchical reinforcement learning framework, where where the agent is decomposed in a high-level policy and a low-level policy. The high-level policy breaks down the goal into sub-goals, more manageable, that are passed to the low level. The low level will execute the sub-goal, and after that, the high-level policy will generate a new sub-goal, and the low level will try to reach this new sub-goal, and so on and so forth, until the hierarchical agent has reached the goal. However, one of the main limitations is that often the sub-goal space is fixed in the implementation, and that is incompatible with the open-ended framework, because if you have a fixed sub-goal space, you are not able to and your agent search for more and more complex goal. At some point, you will need to change so many sub-goals that is not very interesting anymore. So what would be very interesting, that would have to have a sub-goal space that is not fixed but adapted to the goal you are trying to tackle at some point in time. So as we have seen before, open-ended learning process tend to progress toward more and more complex goals, and often these goals are compositional because they reuse previously seen goals to create new ones. And finally, using LLM error agent, as we have seen in the first part, directly, usually they have to face long trajectory, and that means that you have an LLM that is used many times and is extremely costly. In Heraclis, the main ideas are that we want to use a dynamic sub-goal space, which grows by integrating every master goals as a future sub-goal. So when you have mastered a goal, you're putting it in your sub-goal space so that you can reuse it later to tackle a more complex goal. And finally, we want to use an LLM RL as a high-level policy because the LLM is able to accommodate this changing space of sub-goal. And we want to use a simple neural network as a low-level policy to avoid excessive costs. So we'll expose here the 3 training processes that occur in hierarchies. The first one is the training of the high level. So the high level just break down the goal into sub-goals among the usable sub-goals. For instance, in collect food is break down go to tree and cut tree. And it is trained on an error procedures. Then the low level is trained on each of the sub-goal trajectories. For instance, the trajectory for go to tree and the trajectory for cutting the tree. And finally, and crucially in the case of Heracles, we are concatenating all these all the elementary actions made by the low-level agent, the low-level policy, sorry. We're concatenating them and relabeling them with the main goal, collect food, such that the low-level policy is able to, in the low-level policy, we compile the hierarchical policy. And after some time of training, we get a low-level policy that is able, for instance, to collect food here. And collect food can be added to the usable sub-goals. And when the hierarchical agent tries to tackle a more complex goal, such as place table, the high level can directly reuse the sub-goal collect food. What we can see here is the high-level policy has a growing set of sub-goals at its disposal, such that it can tackle more and more complex goals. And the high-level policy is just called every time a few times because the sub-goal space is always adapted to the difficulty of the goal. So you don't need a lot of sub-goals to reach your the new goals you are tackling. So a much more detailed Heracles overview. So here we have, for instance, an autotelic goal sampler, such as Magellan, that selects a goal, place table, that's passed to the high level. At the same time, you have a low-level success rate estimator that will estimate the probability of success of the low level on the different sub-goals that are authorized, for instance, collect food or place table or go to table. And from that, we'll sample some sub-goals to generate a skill space. So the sub-goals that are way more, that have a high probability of success tend to be more often present inside the skill space. And then the high level will select some sub-goals and the low level try to reach them. This trajectory is used to update the low level success rate estimator and also to close the loop. And the high level can then generate another sub-goal. We test our method in the crafter environment, which has a rich structure goal space. So as you can see here, you need, for instance, to go to tree, then collect food to place a table. And once you have placed table, you can make a wood pickaxe. And such environment, we can call it locally open-ended because during the time of the training until you reach the end, the agent is also able to discover new artifacts and new skills as it progress. So we compare our method to different baseline using the crafter score. So the crafter score roughly measures how much of the goal space is mastered. And we compare it to 2 baselines, POAD, that is a GLAM-like method that uses constraint decoding, and FUN, that is a classical hierarchical RL baseline that we have modified just to be its goal condition. And our method outperformed the previous baseline as it used this dynamical sub-goal space. In conclusion, in Heracles, we have shown that we can use an LLM as a high-level policy in a hierarchical RL setup and to accommodate a dynamical set of sub-goals that is always adapted to the task at hand. And so we can easily learn new skills and progress, and because we are all the sub-goals set is always adapted to the difficulty we are trying to tackle. So in conclusion, about this autotelic RL agent, LLM RL agent we have seen, we have first explore how you can ground an LLM by making it interact inside an environment. And we train an LLM as an RL agent, and we functionally ground it through the interaction of the environment. And we show that we can get a system that explores the world efficiently, that is able to generalize between goals. And the natural next step would be to test this system in more complex environments, especially, for instance, in 3D environments with more complex inputs. And that would probably required to have visual inputs in addition to the linguistic one, because describing a 3D scene is way more complex than just the 2D environment I was presenting before. And so perhaps passing from LLM, large language model, to VLM, a visual language model, so having a visual input in addition to the linguistic one. We've made these agents autotelic, like able to choose their own goal by using an LLM to estimate the learning progress and using the LLM as it's able to generalize to unseen goal, such that we generate an efficient curriculum and explore efficiently the goal space. However, in our settings, we needed to have access to predefined list of goals. So we have the list of all the possible goals. And what would be interesting is we'd be able to sample directly, for instance, inside the learned embedding, saying, okay, here we have a high competency, we'd like to know which goal it is, and here is grow elephant. So we'd create new interesting goals without a list. And another method that I've already tackled is autotelic LLM that directly use LLM to generate goals and their reward function, such that the goals have a correct difficulty depending on the learning progress of the agent. It's a work that I did in collaboration with Guillaume Pourcel. And finally, we have made this agent efficient. We have put them inside a hierarchical error framework using a LLM as the high-level agent, high-level policy to accommodate a growing sub-goal space. And we have shown that they can learn new skill efficiently. A next step here also would be to couple this method to a goal generator, because here we have also a list of possible goals in the environments. Finally, this research opens several perspectives. One is about how the collaboration can be made with humans for scientific discovery. So there are already several steps that have been done in this direction with the AI scientists and AlphaEvolve that use LLM to generate an hypothesis about the environment and try to test them and do some automatically some research. But in the team, we also tackled this problem with, for instance, Word LLM, a work that I did in collaboration with Clément Romac and Guillaume Lévy, in which an LLM is used to generate some rules about the word and also to build some intrinsic motivation to discover, to experiments and search more, to get more knowledge about the environment. Another work is done by Julien Pourcel here. It's called ACEs, in which we use an LLM to generate creative puzzles, algorithmic puzzles, and explore the space of algorithmic puzzles and trying to be creative. And finally, another work in the team is the one called Expedition and Expansion, where we use a visual language model to guide the exploration inside the space of continuous cellular automata called Lenia. So it searches a new kind of artificial life and kind of spaces automatically. Another direction is to use open-endedness inside the multi-agent framework. So one of the use that recently is to use open-ended process to identify strategic vulnerabilities in trained multi-agent policies. It's a work from Sam Velayan et al. But what I think would be more interesting, and that have not been explored a lot, or not at my knowledge, to the best of my knowledge, is how, if we imagine that open-ended agent will be prevalent in the future, especially in research or in the daily life, how can such agent can collaborate? For instance, we could imagine to have not only one artificial automatic scientist, but we could have an artificial lab with different specialized scientists that collaborate between themselves and share their knowledge, their specific knowledge. They could also be during this. We could also find a competition framework for several open-ended agents that try to explore the same environments, and that would be a very interesting direction to explore. And finally, last direction would be the human and agent collaboration. If we imagine that open-ended agent will become more and more prevalent in the research. On that last note, I would like to thank you, all of you, for your attention, and also thank the team. So thank you very much. I'm open for your question.
Thank you very much, Thomas. So we are going to go ahead with the question. We start with the reviewers. We start on the one with the furthest away, Pierre-Louis Bacon,
Sorry. So what's the number?
The number, I don't know.
It's
Pierre-Louis Bacon.
yes, sorry.
Bonjour, Thomas. Yeah, Pierre-Luc. All right. Thank you so much. I'm just going to let people keep on clapping here. Sounds good. So thank you so much. Look, the part about hierarchical RL reminds me a bit of the work I've done in a prior life. Although I'm not like actively thinking about those topics, my students keep on bringing me back to that topic. So let's talk about it and see if you can spark the passion again on working on HRL, because it looks like I have no choice but to go back to those topics. So you revisited FUN, which I remember as being basically this goal condition architecture, where if my memory is correct, right, they're learning some sort of embedding and then defining the reward function as some sort of like cosine similarity between what the higher level has told the lower level to do. So can you just go a bit over the details and some of the because you said we adapted FUN. I can kind of see where things have gone. Like you've done some work on learning like meaningful embeddings, but you know, I remember that also the devil was in the details of that paper in 2017. FUN was not an easy paper to reproduce. So can you guide me over some of the details that make your approach work here?
So yeah, so here when it's okay, so here we just have the impression that FUN is not working that much, but it's just before it's way slower, but it's still converge. So in FUN, when we say we just want to make it goal condition, instead of just passing the observation of the environment, we also pass an embedding that have been an embedding of the goals. This embedding is generated from an LLM that is called kind of LLM that is called Quen, and we pass, in addition to the observation, we pass the embedding of the goals, such that we hope that for one kind of goal, the FUN hierarchical agents have learned to decompose the goal I've learned to decompose the goal in sub-goal. I've found points inside the sub-goal space. And we hope that using this kind of embedding, that would help to generalize to other kind of goals to have a fair comparison. However, we did not see that intent to learn different decomposition inside the sub-goal space for each kind of goals. So in not, for instance, reusing the fact that he's already mastered goals such as collect wood to do some place table. We're not seeing that in the curves.
Okay, I see. So because you said like we've modified it so that it receives like an embedding as an input. Like as far as I remember, that paper was also basically learning its own embedding. But what you're saying here is that there's also this additional embedding that you basically concatenate, I guess.
Yes.
And you're hoping that the model is going to learn to extract and leverage that extra information you're passing,
yes, exactly.
right? Okay, that makes sense. You know, I also have students now that have graduated, but they've gone back to these things. They were quite inspired as well by this 2023 paper, Maestro, and so some of the work we started doing is actually I'm kind of wondering what I think about this. So maybe help me about to form an opinion, but I think you're correct, and I agree with you. Like the high level makes a lot of sense to leverage like the rich knowledge encoded in those LLMs. It probably makes sense also to treat the low level as a more basic RL problem. But there's been also a line of work on quite a lot of work on code generation for the low level. So what's your opinion on that question? Like when is code generation versus let's say a more decomposed approach to learning the low level appropriate?
Yeah, yes, it's a very interesting question. Indeed, there is like this two kind of approach. You can either like train via reinforcement learning a low level, or you can just replace the low level by code generation, as it has been done in work such as Voyager.
Yeah,
I think it's very interesting to be able to generate code, and it's even a great idea now that we have LLMs. We can imagine that we can generate powerful codes. However, depending on the environment. It's not always easy to generate some codes that just you just have to make some extra assumption that that's how you can make this code interact with the environment. And it's also not always easy to imagine that for a new environment, for instance, a robot interacting with a real world, finding very different part of the environment, perhaps it will be difficult to ground the code you are used to generate to this new part of the environment. So we just propose a method that avoid that, even if code generation is very powerful when we have sufficient knowledge about the environment. For instance, if it's in a game, you can imagine that it's very interesting tactics. Here we are using a bit less assumption, and we are saying, okay, we just try to learn using a basic interaction with the environment.
I see. Because one of the like I'm really in that position these days. I'm having a bit of an existential crisis as an RL researcher and trying to think about where we're going to go in the future. And I think a lot of your thesis brings a perspective in which we use our LLM for the heavy lifting of the RL problem, which I think is actually in the specification of the problem in a way. And I'm just thinking out loud here, and maybe help me make sense of what I'm saying here. So it looks like the systems you've built are essentially allow you to generate reward functions in a way, but they generate them in a specific way. In that it looks like your reward functions seem to be like goal achievement type reward functions. But we could think of other ways maybe to define goals and basically reward functions, basically. So we just talked about code generation. Another way to go about this would be to, let's say if we were to use code to literally have an agent generate the code that expresses the thing we want to do. So how much of a general language is how much expressivity do you have in that framework? What are the pros and cons versus like goal achievement versus more maybe, I don't know, perhaps more expressive or different ways of encoding and having our agents generate their own reward functions?
Yeah, definitely. Great question. So yes, in all my works here, I directed my work toward like goal achievement, as you said, usually in sparse reward kind of way, where you have just one goal, and if you succeed, you have just a reward of 1 and either 0. It's mostly because it's we did that way because it seems more natural at the time. I did that because usually you can imagine you have a trajectory and you want to decompose it in several sub goals, or you want to reach one specific goal. So it was mostly because it's easy to interpret goal that way that we use it.
Mm-hmm.
So for what it is about other kind of goal, it would be more difficult to express because, for instance, if you want to use the Magellan method, for instance, it's great if you have this kind of definition of goal. You just have a sparse reward, and that helps you estimate the competency. So I think all my line of work is oriented in this direction because it's very fruitful. It's easy to get some information about the environment that enforces a structure over either the goal space, the environment generation, or the goal space exploration. That is very interesting to leverage. So that's why we use this structure.
Okay. Because like I'm wondering, let's say we think concretely, we have something like the pendulum or pole balancing task, right? These are sort of physics based problems, and I'm wondering whether like let's say your LLM probably knows about physics a little bit somehow, right? Like it knows how things general laws of physics, or maybe knows actually symbolic laws of physics that could inform the design of maybe a better like shaped reward function. Who knows? Like let's say for the pendulum, maybe it would come up with a reward function that says, oh, it's good when I don't know, the position goes up a little bit, right? Instead of being fully sparse. So I'm wondering if yeah, I'm wondering if we lose some of that ability to leverage prior knowledge in using that that type of reward function that you've been exploring.
Yeah, that's very true. Like if you imagine that you can have more knowledge about the environment, you could imagine an LLM that is able to generate perhaps a richer reward function. A counterpoint that you could bring here is just to say, okay, but we can just break down this this complex reward function in smaller reward functions that are sparse but over a short period of time. Perhaps if you imagine the different angle of the pendulum, first reaching having some reward for being in this angle, and then getting more reward for getting in this angle. So you could have like kind of a dynamic way of generating reward. I've reached already this part, and I want to reach this more complex goal for balancing. But definitely, if you have an LLM that has a lot of information about the world, and we know that in reinforcement learning, that is very important to having this kind of reward, a very dense reward, help a lot the learning. Here we have done tricks to avoid that, but indeed, if you have some knowledge, additional knowledge about the environment, that could be a great way to leverage that. So in principle, if it's possible, we should do it.
Okay, sounds good. Last question, and then I'll let other members of the jury ask their questions. I was just curious and a bit concerned in the work on World LLM. So you're talking about using Metropolis sampling essentially for uncertainty, what seems to be like uncertainty quantification. I think it's fine. It's sound, but I'm just like wondering, uncertainty quantification in LLMs is, as far as I understand, very much open-ended, very much difficult. So can you give me a bit of a reinsurance regarding the feasibility of that approach at scale and yeah.
Yes. So in this work, we've used an LLM to generate some rules, and then test these rules using a Bayesian approach, and doing some sampling to verify if some rules help to predict some transition in the environment. And sorry, can we repeat your question?
So if I remember, I'm reading my notes here, and you're doing, as far as I understood, you were doing some sort of uncertainty quantification using Metropolis Hastings type sampling to, and yeah. So I'm wondering like how scalable that kind of approach is, and it just doesn't sound like it's something that would scale very well.
Yes, so here it was kind of a first work. We're using very simple method here to do this quantification. Indeed, that required a lot of samplings, and other like further approach would like probably change this kind of quantification with other statistical method like Thompson sampling or things like that to improve the quantification of the uncertainty. But here it was more to demonstrate that we can use an LLM to generate rules and quantify how much the rule explains the environment. So it was a first approach, a first taste about that.
Okay. That's good, because like the same pipelines are also used in drug discovery, material discovery, and yeah, I think it's still a very much a big deal to be able to get some sort of confidence or uncertainty quantification over what you generate. So I would have been happily surprised if you had found a solution to that in while working on this.
Unfortunately, we're just like reusing some classical technique just to verify the whole framework is working and understanding it. It was already fairly complex to make everything work together.
Okay, I'm kind of done with this, but there's been work also where people literally just ask their LLM to output confidence scores. Of course, these scores need not be calibrated at all, but yeah, I don't know.
I think yes. Here we did not test that. We wanted something that is at least a bit statistically sounded, and just because we have to do them to eliminate some impossible theory, and also being able to quantify how much theory is impossible, and that's why we use this kind of approach.
Okay, sounds good. Thank you. That's all for my questions for now. Thank you.
Okay, thank you. So now we go to Georg Martius to begin.
Yeah, great. Thanks, Thomas, for the wonderful talk. I'm really amazed by your work and how nicely you have been presenting this in your presentation. I would like to ask a question about the GLAM part, this GFLAN, the first part of the talk, where you're using PPO, right, to update your agents. And I was wondering now in LLMs, people are also using GRPO. And I was wondering, maybe, I mean, that was not existing probably at the time. I just wanted to know a little bit what you think about these different methods and whether you would maybe use that now.
Yes, that's a very interesting question. Indeed, right now, a lot of people coming from NLP trying to apply some RL methods are using GRPO. GRPO is been well designed, from this kind of bounded problem where you have a question, mathematical question, for instance, and you have to generate a solution in just one go. So GRPO usually required that you do several rollouts for the same questions. And it's not evident that inside an environment that would be a great idea to approximate the value function, or is here the advantage function doing this kind of rollout, because that means that for any interaction with the environment, we'll have to redo this rollout. It will be very costly. And thus, I've read with a lot of interest this GRPO paper, but usually when you have the point of view of interacting on multi-turns inside the environment, PPO seems still a lot more appealing.
Yeah, no, I agree with you on this one. Value functions still have a role, I guess. Very good. Now, you had a place in the thesis you were mentioning, like you had this experiment in the paper where you flip the meaning of one of the actions here, and then you show how this evolves. And it was interesting to see that, I mean, clearly there is some kind of drop in performance, but I would have kind of expected that this drop just disappears with fine tuning. But in your plot, it suggested that there is a gap remaining. And I was kind of wondering why this is.
Yeah, I understand the question. But here, so we did the experiments in 0 shot, just after the training of the LLM with the error interaction. We just directly test in 0 shot by changing words, by new words or unseen or not existing words. So sure, if you do some fine tuning, you will see probably this gap disappear. This gap appear only in 0 shots. So the idea was just to test if you have grounded not the words, but you have do some functional grounding on the environment. So you are there is a little bit of perturbation when the words does not exist at all, but it's still able to retain very strong performances showing this functional grounding.
Okay, but wait, so this is mostly kind of showing that this embedding space of the LLM is kind of nicely used, I would say somehow. But my question was rather about a figure where you are swapping the action meaning. So the meaning going left and going right was somehow swapped. Maybe it was not in this particular environment, but I think it was here. And there the performance kind of somehow did not recover, and I was kind of wondering why this is the case.
Yes, sorry. So when moving from new actions some to synonym actions is what you are telling about. So yeah, here as we have as I've explained before. We were kind of perplexed first when we changed the action by synonym actions. We thought it would be easy to get very good results. And when we observed this very, very poor results here with a big drop in competency. So once again, it's in 0 shots. So there is no fine tuning on this new synonym actions. And in the paper, we link that to overfitting on the tokens that have been used. We have trained the LLM just on 6 or not 10 or 20 tokens in total. And we've trained it for thousands of steps, so kind of overfitting, and perhaps there is kind of decorrelation between the action that have been trained and the synonym actions. So we are not recovering something that we could expect. And we have shown that indeed in another paper, the LLM tend to overfit to the prompt, the LLM ARL agents. So it's less surprising right now to see that this overfitting also occur on the actions. So perhaps a way to mitigate that, in addition to this contrastive loss, would be to have some to select not one kind of token, but for instance, selecting move ahead and go forward as synonym possibilities, having a richer action domain with several synonyms.
Okay, good. Okay. I would like to continue on this Magellan work, which I find super exciting. I've been also working with learning progress estimation and so on, and these estimators are traditionally difficult, right? Or inherently, let's say, inherently difficult, not inherently difficult. And I really like this nice approach of keeping these parameters from your competence estimator around. If I understand correctly, these are the LoRa weights, right? Only the LoRa.
Yeah. So a thing that I did not explain during the presentation, and I just say, okay, we train an LLM and we keep the weights. Big LLM that would seem very costly to store billions of weights. So what we are just doing is we are using LoRa adapters. So LoRa adapters, for the one interested, are a method that just add parallel weights. So sorry, I bring that here. So you have the pre-trained weights of the LLM, and you are adding some external weights that will be the one that will be fine-tuned. So it's a bit more costly in the forward, but during the backward, you just have a few weights to train and not the main weights of the LLM. So here we did the same. In Magellan, we just kept some LoRa adapter that we have trained at time t. And when I say we store the weight of the LLM, we are only storing the weights from the LoRa adapters. And we train a LoRa adapter at different time steps. So that's why that's what we're keeping inside buffers. It's way lighter, way lighter, yeah.
Great. But now, let's say, how did you choose the capital N, right? So this delay between these 2 points, was it something that was actually quite difficult to fix, or was it easy for you to find this? Because I somehow remember that it was always a bit finicky to sort of estimate these deltas.
So we did some EPR parameter tuning based on the data we have already collected. I think we have perhaps at the beginning I've just a bit overshoot doing some high rate of collections, and then we test different parameters until we find a good N. So it's mostly EPR parameter tuning here.
And was it very sensitive, or?
No, it wasn't that much sensitive. It was kind of robust.
I see. But what is interesting in your method is that you're asking this competence estimator on goals it has not seen, right? I mean, that's the whole point, right?
Yes, exactly.
But nevertheless, I guess there might be some goals which are completely out of training distribution, right? So you have absolutely no clue about them, and others which you are. And so I was wondering, do you think there would be a way to also incorporate this, let's say, keyword epistemic uncertainty of your estimator?
That's a very interesting question. The first point is you could imagine that first, like inside the herbivores, you could have like a subcategory of herbivore that doesn't from which the competency does not evolve the same way as the others, like a subgroup of herbivores. So that would be a bit more complex. And we could imagine that at the beginning it just generalized over all herbivores, but the LLM sampling like our method Magellan sampling some goals and then discovering that they are not having the same behavior, we'll just learn to classifying them a bit differently. Perhaps there is a rule that explains how they can be classified, so they can push it over. Or that for the method can at least give a guess for for goals that are completely different from the one you have trained on. For instance, we have trained it on growing herbivores and carnivores and plants. We have never asked it to grow a castle suddenly, but probably you can put it in the goal space. Usually what happens as a dynamic, what we see as a dynamics is, because I've just seen at the end of the training, but during the training, usually what's happened, it's the goal that are not mastered yet or kind of new are just put in the zero competency. So kind of by default in zero competency. And we have like a uniform kind of exploration. So it's still a weakness here to discover inside these goals and select some of them. And if we get some signals, they will be moved very quickly indeed during the training. If one goal suddenly that was categorized as zero competency has a little bit of success, it will be moved kind of quickly closer to this border here, where there is a bit more success. And then will be trained a bit more and better characterized. But there is no inherent mechanism inside Magellan to have some general uncertainty over the full goal space. So yeah, I think it's
Good. I wanted to maybe paraphrase your answer in a way that you say, even though I don't have any explicit knowledge of the uncertainty, since I'm only comparing the answer for the same model with the two different time steps, sort of you're kind of hoping that this will still behave reasonably well, right? Even for goals it hasn't seen. Is that kind of correct paraphrasing, or? Yeah,
it's a correct paraphrasing. It's just like we could imagine that we train the same model either on a larger goal space, such as it's able to generalize to a new goal, be able to generalize to more different kind of goals. But here it's truly a metacognitive setup where you have here the LLM that's both estimates its own ability to reach some goals and at the same time try to act inside the environment. So it's not like you have trained an estimator for any kind of agent and you can change it suddenly, unplug it from an agent and put it on another on completely different tasks.
Yeah, sure. Maybe can you go to slide 57, which is just a few slides ahead here. And so I was a bit wondering, and maybe you can tell me a little bit why it, let's say, takes thousands of iterations here, although I only have essentially 5 objects I can interact with, right? I have these different things I can combine, and maybe you can elaborate a little bit of what is the kind of the slow part here. I mean, the LLM, I guess, doesn't need so many, right? It just
exactly.
So maybe you can a little bit elaborate on what is the problem here.
I've spoken about like different categories like baby herbivore or carnivore, but inside each categories there is more than like 10 or like 30 different kind of objects. So you have to learn to cut how they are related, and you also you have to learn how for instance, how they interact between themselves, because you have kind of millions of possible goals. Your agent also has to learn to do this generalization to another level than what has been done in GLAM. In GLAM, there was like thousands of goals, and here we have millions of goals. So it's way more difficult. And that's why it's very important to as quickly as possible, remove the impossible goals and characterize them as impossible. So, and to do so, first, the Magellan need to characterize which goals are impossible, and then also be able to build the curriculum, because at the beginning, when you are just trained by randomly, you will mostly stumble across impossible tasks.
So maybe then let's open this up a little bit to a slightly more general question. Is kind of right here, you are creating all these impossible, like all these goals, and many of them are kind of crazy and you can't really create them, right? In this environment, maybe in the real world, there are also millions of things you would love to do, but you can't, right? And And so maybe what is your perspective on kind of either creating these goal spaces and then sampling thousands of goals which are like infinite goals which are not possible, and then trying to chop them off, rather than I mean, in classical RL exploration, you kind of go the other way around, right? You're going forward and trying to see what you can do. Here you kind of go the other way around, right? You step into the future and ask yourself, what I could do, and then you try to do it. So maybe you can link a little bit these two approaches and say when we might have also chances to.
So here, as I explained, we've used the list of goals because we are not using like a goal generator. So we have, because usually in this kind of situation, there is like a lot of possible goals. Like the goal generator would have to learn the underlying dynamics of the environment to stop generating goals that are impossible. So because we are not using a goal generator, we have used this way of just generating a lot of possible goals and just try to chop them off. But a kind of reverse dynamic, if we have replaced that by a goal generator, would have been like to learn similarly that, for instance, you should not generate the goal grow a carnivore if you don't have a seed into your environment. So it's kind of a mirror problem that we've put here. But we have alleviated from the issue of learning to generate goals. So that would be my answer here. Even if, so that's why we start with this very big list. And you have to learn to, but in reality, and that's why I explain in the conclusion, perhaps if I go there, sorry. So yeah, we could imagine that we start with a small list of goals, and then we just learn to have this embedding space, and from which you will try to learn. And the next step would be to learn to directly sample, avoiding to sample like impossible goals that are in the blue region or probably less interesting one, and directly sampling interesting goals. So you could start by building this embedding space with fewer goals that are perhaps given by humans, and then you start this process, and then you sample directly some goal that could be another possibilities.
Very nice. I don't know, in the interest of time, shall we move on now? Or, I mean, I have more questions, but maybe I can just leave it for this now. And if there's at the end need to ask more questions, I can. Okay, let's do that.
Okay, thank you. Let's do that. So now let's go to the examiners and start with Martha White at the University of Carta.
Great. Yeah, thank you. Just like everyone else here has said, thanks for the very nice talk and the very impressive work. The scope of work that you have done here is quite amazing. So I very much support the overall framework. I really like what you're doing here. And now whenever you put these kinds of big systems together, there's all these really interesting details. So I'm actually just going to dive into asking about very specific details, knowing that the overall, I'm very impressed by all the work you've done here. Okay, I'm not going to do this perfectly in order. I'm actually going to start with Heracles at the very end and then come back in order afterwards. The part that I didn't fully understand how it was done for this, well, actually, I'm going to say there's lots of parts that I didn't understand. There's lots of interesting details here, but I didn't understand how you learn the low-level policy. So you have the simple neural network, that's the lower-level policy. What algorithm was used there, and how did you do that?
So to train the low-level policy, I use the IWR policy. IWR algorithm. And the idea was we can put inside the buffer of trajectories that is used to train the agent. We can put both kind of on policy trajectories that are just collecting when we ask the low-level agents to unfold the trajectory, and we can also add some more off policy trajectories when we just concatenate all the basic actions and relabel them with the main goal. So the idea is you train it as a goal condition agent on all these kind of goal, and it both continuously improve on the goal is already mastered. For instance, here go to tree and cut tree, and learn new goals at the same time, like collect wood. So yeah, it's how we train it.
Okay, got it. And so I guess you used a standard goal condition algorithm. Then how did you deal with partial observability for that algorithm?
Sorry?
How did you deal with the partial observability? Presumably this crafter is a partially observable environment.
Yeah, so here I did something very crude. I did not treat it at all. I did not put some recurrent neural network because it was difficult with this of policy framework. And because I've already seen that you can train in Crafter without treating this kind of partial observability, just observing the last frame. So you are doing probably less efficient trajectories because you can probably forget that you have let something on the table and you have to re-explore the environments. That is true, but it's still kind of able to learn. Probably if we do that's on more complex environment, you will be forced to treat this kind of problem. So either by doing putting some recurrent neural network, but that seems complicated. An idea that I have is just like perhaps changing it by a kind of a small, I can put just the past 5 or 10 frames as an observation. That would be easier to deal with a recurrent net. So yeah, that would be an idea.
Yeah, that makes sense. Using a little bit of a history. And I guess I like your point, maybe that each of these subproblems is simple enough that a more basic agent actually might be effective. That's interesting. It is true that recurrence in RL is a bit of a pain, although I do think we're starting to get some advances there. So maybe that's something to revisit in the future. Okay, jumping all the way back now to page 37. Let me just acknowledge that I am not an LLM person, so I actually appreciated reading this and seeing how you're using LLMs in this way. So in general, I have sort of a conceptual question on this. I see how you used these probabilities. So, the network is going to output the probabilities over possible next words. That's going to be much large. I'm going to state what I believe is happening. I believe that means that's going to be a much larger set than you actually care for your actions, but then you're only going to look at the log likelihoods of the actual action set, which is a much smaller set, and you're going to be increasing the likelihoods of the good actions and kind of ignoring all the other things that the network is outputting. Is that right?
Yes, exactly.
Okay, yeah, I guess my implicit question here is there any when do you expect this to work well, and what do you think are issues with this idea? It feels like we were taking this much larger model and then using it for a very small set of things, and in some sense using it for a different goal. Like, now we have these rewards and we're trying to take these actions. I'm curious if you have any intuition about when this why this works well, because it does clearly work well, but then also when it might not work so well.
So yeah, so here we are using an LLM to directly kind of model the probability of an action. So that's true that we are just trying to we just tackle few tokens here, and that seems like using this big network just for 6 actions. However, you can imagine that the same system can calculate at the same time way more actions, just because inside in our first test, inside the simple environment that is BBI text, we just need 6 actions. So perhaps it's a bit overkill, but we are not using even like that big of an LLM. We are just using 700 million parameters. That is not that big anymore. And what is working very well here is because at the beginning you have an LLM that has already like good prior about the word to do this exploration. For instance, if I say, okay, you have to reach this red ball, and this red ball is 3 steps forward and 1 step right, and it's behind this cube, the LLM will output a trajectory that is mostly consistent with its description and will send you in the right direction, so you will be more efficient. So that's one of the reasons that the exploration is very efficient for such a system. But at the same time, this system will work poorly if usually that kind of define the intuition, because when you have a classical RL agent, it will just first explore the environment kind of uniformly. So it don't have a lot of prior, it don't have any prior about the environment. But if you are asking such a framework to search, for instance, an object, for instance, a knife, and it's not in the kitchen, but it's probably in some very strange part of the garden, because the distribution is so picked around such certain token for pushing in the exploration in just such a narrow spaces. Usually the exploration, if it's out of what's inside the the biases of the LLM is very poor. Yes, we can imagine that with time, as the entropy will augment, you will have a flattening, but it's not very interesting anymore to have an LLM. So it's a true question how we can do that. Usually, when it's not an error setup, what is done is just giving the past part of the trajectory to the LLM and ask him to do some reflection about it. So incorporating that could be a solution here.
Okay. Yeah. Okay. Yeah, your answer makes a lot of sense, actually. I'll ask one more question about this. This might actually be in your experiments, but did you take the LLM and not do any fine tuning, but just query the probabilities as is?
We did not compare it like to an LLM directly in zero shot, to be honest, in this experiment, but we'd have probably more than what would be possible in random. As I said, we have observed that the exploration is kind of good at the beginning, so there is already a good bias. You progress kind of quickly compared to other structures. So probably you would have like, and we can observe that also on other paper that are not using RL, but directly using the LLM. We observe like we have already good results. The idea here in this paper is less to observe that an LLM can do this expression than ground rule of the environment inside its weight to be able to generalize some goals, for instance.
Fair enough. Okay, great. The next section here is about the world LLMs, and very interesting work. Yeah, trying to get the model to be more accurate by actively going and getting what it doesn't know is clearly a useful thing to do. And now, in general, when I'm thinking like world models or forward models for RL, I'm then thinking you're going to use those for planning in some way, or you're going to use them to update the RL agent itself, like learn in that. Is that how I should be thinking about how you're going to use this world LLM eventually? Like this work was about learning it, not about using it.
Yes, I will move to it. So yeah, here the idea was like to build a word model, but the idea is, can we like extract some rules given by the LLM inside an environment? And can we use it like to push it to exploration? Because here we have an agent that try to discover rules that are not predicted by transitions that are not predicted by the current rules. So there is this arm race between the scientists the LLM use as scientists that try to generate some interesting rules, and the agents that try to discover a new transition, and you get a reward for transitions that are not explained well by the rules. So yeah, you can imagine that as you are building this kind of framework, you can also reuse the rule to explore more complex environments. Because if some rules finally are like kind of validated by the statistical part, like they are never rejected, you can use it for doing more exploration. For instance, when you know how to combine water and seed to get a plant, and you know that it's a kind of a rule, you can reuse that to do some better exploration and directly say, okay, I want to do a plant and try to that on a baby cow. So certainly that would be a very interesting follow-up to this paper.
Okay. Yeah, maybe the question I was asking here is that, yeah, I know you have an RL loop here. So like in a sense, you're using this to learn this model, but then of course you could use the model to solve tasks or, give the agent new problems to solve. And presumably that's what you would eventually want to use this world model for. Is that right?
Yes, exactly. And at the same time, you can also imagine that you put this agent inside a complex environment that human does not understand fully. And because the experimenter that interacts with the agent will build the internal world model, but it's not explainable in a sense. But here, the scientist, because it's building rules with language, would be like something very interesting, like to have for humans to have this kind of agent that explore the environment and learn to generate some rules, and then the humans can directly learn, look at the rules that have been generated, and that seems pretty solid, pretty strong to explain the word. And that would be another interesting approach and an interesting use of this work.
Okay, I see. Yes, you could give a more interpretable or explainable agent.
Yeah.
Yeah, I guess one of the things I was going to ask you as a follow-up here is if you use this world model, I mean, one of the biggest issues in model-based RL is we can make our models more and more accurate, but it doesn't always result in good policies because small errors or mismatches between the model and the actual environment or the real world can cause really big differences in the policies or issues when you're bootstrapping. So I was just curious if you thought that this strategy was also helping towards, let's say, a model-based RL algorithm that would later use this model.
So yeah, so first we have these dynamics where the experimenter will try to falsify the rules that have been generated. So in a sense, the rules are currently permanently tested, so they are pushed forward and further and further into the boundaries. And so usually like rules that are highly specific, for instance, not especially about water or seeds, but you could say if you are in a scene where there is a cow and you put water on seed, the seed grows. It's a rule that is less general and will be more brittle. That if you say just water on seed will generate a plant. So you have this first aspect where you are testing your rules and try to refine them through this approach. And then when we have generated this rule, that would be indeed very interesting, like to use it inside an agent to try to explore or to say, okay, at some point I've generated all the possible rules and I want to do some new combination of objects inside the environment, is hoping to find new difficult places. So that's also a way to intrinsically motivate the agent.
Okay, thank you for those answers. Okay, I'm going to jump to page 73 and figure 8.1. This was, I believe, with the Magellan. Let me scroll.
73, sorry. 53 or 73, sorry?
Yeah, page 73, but not of your slides, rather of your thesis.
Yes, sorry.
But it's the Magellan architecture. So like it's this metacognition, which I know you have in your slides somewhere.
Yeah, exactly. Yeah.
In general, I really like this architecture. Like I think it's a nice idea. I'm curious if it's strictly tied to LLMs. Like this architecture looks like it could be just a generally useful one for CraftX, for example. Is that right? Like, do you feel like LLMs have to be part of this, or could you use this architecture without it?
No. They don't need. It's not required that they are part of it. There is an important hypothesis that is there, is that because you're supposing that you can do some generalization between goals, you need an agent that is also able to do some generalization between goals. If you're an agent that is not able to do that, it's no use to have this kind of architecture. But the LLM is just because it's an enabler here, because as I've shown before, language is a very powerful tool to characterize a goal space and also to leverage some clues. But you could have like other structures. If you have similar statistical clue inside them, either with a pre-trained model or a learned one, that could be as efficient.
Okay, nice. So I think I get it. Yeah, the LLM is providing you essentially this representation where it's generalizes nicely in goal space. And once you have something that generalizes appropriately, it makes everything else in RL so much better. Okay, so I like that. One other specific question for this. You have the goal selector as a multi-arm bandit. What's the specific algorithm you use there?
So we're just doing some epsilon greedy exploration. So we have we do some sampling over the goal space. So we have and the probability is just the softmax of the learning progress over the goals in the goal space. And once in a while we do some uniform sampling over the goals. So probably it's not, there is probably more sophisticated technique. We just use something very simple because here the idea was to explain this kind of, was to mostly focus on the competency prediction. But after that, we just use this multi-arm bandit setup, where, as I tell you, we do a softmax over the learning progress to get the probability of each goals. So that's also required to do some measurement for all the goals in the goal space, and it's one of the costs. It's still not that a big not that a big of a cost, because you are not have to train or to test an agent on all the goals. It's just estimation, but it's still a big part of the cost. Sorry.
Okay, so yeah, does that mean that you're essentially putting a softmax as if it's on the values, like you're using this learning progress as the values? You just put a softmax on top, plus maybe an epsilon greedy step every once in a while. There's no learning in that box. It's just
no, not at all.
Okay, neat. Yeah, I can see why you want to try to remove some learning in different parts and just keep it as a fixed strategy. So that's actually quite sensible. Okay, my last questions are about chapter 9 on two very specific questions. One is in the definition for the goals and rewards. Okay, I'm gonna keep scrolling. The definition.
Sorry,
one.
chapter 9 is about which work? Sorry.
Oh, it is about the what is the exact?
LLM.
Ah, yeah.
Okay, let me just see. I guess I just had a general question that in this definition in section 9.4, there was a definition for the problem setting. So you had an MDP with a goal space, and R was the space of binary reward functions about whether you achieve that goal or not. I was just curious about if you've considered a setting where the reward isn't just binary, as in like you could have intermediate rewards on the way to goals.
Yes, I think it's related to the question that Pierre-Luc Vegan has asked. Yeah, we just thought something very simple. This binary reward was like a simple idea, and we did not consider more complex form of reward. The idea being like as the autotelic LLM architecture will generate more and more complex goals. In a sense, some goals will be reused and into the more complex ones, but you are not getting some partial rewards as you progress inside the goals that have been generated here. We are just considering in this work a binary reward for simplicity.
Okay, simplicity is a fine answer. I mean, there's lots of different ways to achieve goals, and so I do think that those goals along the way are important, but then it does actually result in these difficult questions around, okay, then how do you still encourage it to reach the goal, considering you have to balance the rewards along the way? So simplicity is a fine answer. You have thought about it, but decided on simpler. Okay, very last question. You use PPO largely everywhere, and I get that because you're fine-tuning LLMs. Did you ever consider other algorithms?
Yeah, so
not just GRPO. I know GRPO was asked about as well, but maybe like there's just a large number of RL algorithms like soft actor critic or those kinds of algorithms.
Yes. So we did some work with Loris Gavin that is not put inside the thesis when we did an adaptation of soft actor critic for a GLAM-like algorithm and we get more sample efficiency. But in the end, I mostly used during my thesis PPO derived algorithm, and even in a sense AWR it's close in some principle to PPO. So that's yes, I think it's because I think I get used to this algorithm a lot and I use it a lot, and it's very efficient, and it's also a kind of efficiency measure because I know how to debug it and I know its behavior, and that's helped me a lot. Also, its own policy nature. It's interesting for a lot of the setups we are seeing here. So that's why I selected in most of my works.
Yeah, that makes sense. Okay, so you're sort of saying the same things I've heard also from others anyway, who try to fine-tune LLMs with RL, that this on-policyness of PPO is important. Okay, that was my last question. Thank you.
Thank you.
Okay, thank you. So the last examiner, so you have used so that don't go 3 minutes.
Yeah, so Thomas, fantastic talk, great thesis. I was really impressed by the coherence of the work and the diversity of the work, and it's not easy to get both of those things to come together. I will, obviously the other examiners have asked some great questions, so I'll try to ask some questions from slightly different angles. Perhaps a couple of synoptic questions, first of all. So in many of the works that you've done, you've needed to construct environments to demonstrate the effectiveness of the methods. And in particular, these environments share the property that you know what the discoveries should look like as the creator of the environment. I wonder whether you can comment on how you could extend these environments or construct an environment where the agent could in fact surprise you and go beyond your knowledge or make a discovery you hadn't previously envisaged.
So yes, indeed, in order to make the control easier, we tend to use this kind of environment where we know where we are going, and we just let just let the agent try to explore. As I tell before, the hierarchless kind of environment, I call it locally open-ended, because the agent kind of explore, and for sometimes we'll discover some artifacts by itself, but we know where we're heading. So one of the interesting environments, even if it's in Crafter, one way to get beyond that is first with autotelic LLM, because we let an LLM to generate more interesting rewards. So we get to some point where you generate something that's called a shelter, and you can also generate a cave or a bridge. So in a sense, sometimes you're surprised by the kind of definition, because you can say, okay, a castle is just 3 blocks. So, but this was kind of a limit case when it's not even doing really what you want. There is also an idea of alignment between how you call goal and how difficult it is truly. But yes, this work in a sense was a work where we get generation of surprise. But I think when I think about being in an environment that will generate some surprise, I think about this kind of Magellan environment, because the environment we use, Little Zoo, is not very surpriseful, that's sure, but we can imagine to use Magellan on more complex environments, for instance, Minecraft. And through the sampling procedure I was telling about, like when we have trained on several goals that are already well known, we can imagine, okay, I want to select this point that I don't know, but I know there is interesting competency probably there, and hoping for the best, hoping for discoveries. And that also already, that's, I think it's an interesting way to generate interesting goals and unthought of, but you need a rich enough environment such as Minecraft.
Yeah, for sure. It occurs to me that even beyond that, you could use Magellan for computer use or tool use or something like that.
Exactly.
Which would be really, really cool. And potentially we'd have to think about safety there as well. But, maybe you can stick on Magellan for a moment. Obviously, the central challenge here is learning progress, right? And one of the assumptions you make is that you can predict future learning progress by reference to the past. The challenge of this is that you might miss second derivative effects. So, if your learning progress is tailing off, for example. Can you comment on whether there are ways that you could improve upon this prediction of just taking the past, the recent past learning progress as your regression target?
So in Magellan, indeed, we have just do like this very simple, that is used to usually to do this competence estimation, and we just do the difference between the two. I think like right now, I just have not a very strong idea about how we can push it to a higher order, but I think we should, for instance, more reuse the embedding space we get along the way. For instance, and a point, for instance, is when we want to reach a goal inside the embedding space, you could say, okay, I will have some goals in between, and you have this kind of curvature, if we are putting it in a higher dimension of this embedding space, where you have some geometry, so you have more information than just about one point, and you can perhaps extract that to say, okay, perhaps it's a part of the goal space that is very complex, and perhaps you can say there is high uncertainty on this point, and or there is a part that seems kind of well mastered, where there is no evolution through time about the learning progress. Mm-hmm. So perhaps that would be a manner to better refine the prediction of learning progress, because indeed here with Magellan there is no idea of the uncertainty about our competency. We just say, okay, it's our competency, but I think we can leverage so much more from this space. As I said at the end, we have both information, semantic, and competency. So we should leverage it.
Yeah. In some sense, it should be aware of this.
Yeah,
that you have made.
You can make a little ball around a goal and say, okay, perhaps if there is a high competency here, but around it's very low, it's kind of strange, and we should manage to change it.
Yeah, that makes perfect sense to me. Can I ask a question about the results in Magellan, maybe for my understanding? So you had this I think I don't know whether it was on here, but at least in the
this one?
Yes, it is. No, that's
Right.
right. It is that. It's the EK online out,
Yeah.
which is the best performing
Yeah.
here. Now, I was half expecting that if you went to a large enough number of episodes, then Magellan might even outperform this, because perhaps the expert knowledge is doing some kind of imperfect grouping here, and in principle, you know, Magellan should be able to discover something that's a better grouping than this. Is that just a limitation of the environment? Do you expect that if the environment were more diverse, then the kind of fixed grouping would be exceeded by Magellan or something?
Yes, exactly. So here, perhaps for the people, so here we are using a simple environment that's allowed to have a very perfect expert. We know the rules behind the environment. But as I told before, in an open-ended environment, we do not suppose that we are experts. But even without speaking about open-ended environments, we could imagine like complex environments, complex enough such that human expert can help, but they kind of fail. And we could imagine, like, it's very probable, because if Magellan can tackle enough goals, perhaps he will be able to find by himself some rules. So first, probably re-extract similar rules and then go further. Especially because I think it's able to tackle so many goals at once and restructuring the whole goal space at the same time. So probably that will help him discovering the rule, because fundamentally what Magellan is doing is trying to understanding the underlying rules of the environment to explain the world. And I think there is some things that would be of interest here. If we look at the impossible goals, yes, sorry, it's very overexposed. So if you look at the impossible goals here, first it was just grouped as impossible. But if you look exactly what kind of impossibilities, you see that there is several clusters of impossibility. And what's very interesting, and we found in Magellan, is they are not just randomly grouped. They are grouped by why they're impossible. So to be able to generalize why a goal is impossible, you need to understand the rules. For instance, you are lacking some water, and so it's from the start impossible from the get-go for growing anything other than grasping water, or you are missing a plant, or you are missing both of them. So it's way more powerful, like, than just trying to predict some competency. In doing so, it's also able to leverage the structure of the LLM to find the rules inside the environment. So I think that would be very interesting also to reuse it later on other experiments.
Yeah, you could use that. I mean, it feels like it's got a flavor of being able to model the limitations of scientific experiments or something, if you were to apply it in that kind of realm. Maybe I can ask about eager, because nobody has asked about that yet, which is in, I can't remember which chapter of your thesis, but later chapters of reward shaping work. I had one question about that, which is, in that work, you are relying on this set of trajectories from a bot in order to train the model. But there's kind of two issues with that. Firstly, if you've got a bunch of these trajectories from a bot, why not just do behavioral cloning anyway? And secondly, in general, you might not have a bot that's available. Is there some sort of alternative to having to pre-warm everything with these set of expert trajectories that still has the benefit of being able to kind of get the reward shaping up?
So eager was kind of a preliminary work on this. This idea was we are not using an LLM here. We're trying to just use some statistical rules about language and try to leverage that. The interesting thing is, we have to program it with a bot, but it's just with very few trajectories. It's a small number of trajectories just to extract some general rules, and then from that you can go to more complex setups. And so it's one of the things we show in the thesis, that we just need some of them, and when we compare to other methods that we use way more trajectories, we are in some small sample efficient even if we include this kind of samples. You could also imagine, like, in a more complex setup, that you explore the environment and you will keep in our archive some correct transition by yourself, and then retrain on your own transition. That would avoid using a bot. It just like this pre-training help help for starting the full training. Indeed.
Yeah, that makes sense. So yes, you think of it like a pre-training method, and then you could just bootstrap from that point on. Okay, maybe there's a couple of questions left. So maybe one on Heracles. I thought this was very impressive, interesting work. You point out a particular limitation of this, which is that you're distilling the high-level behaviors into the low-level controller, right? But as the skills get more complicated, the time horizon will increase for these skills. And that might, make it harder for RL to, in fact, learn the low-level skill. And maybe even that exceeds the step limit, because you've got this fixed step limit K, right, for the low-level controller. Can you comment on how you might overcome that problem if you were to extend the work?
Yeah, that's very interesting. So it's a true limitation in the sense that if you want to, the low level finally have the same problem that the general error problem when you get longer and longer trajectories. However, here the noise to signal ratio is way better because you are using a hierarchical policy, already finding good trajectories on which you're training your low level. So you already are kind of good on this kind of thing. And my second step is like the low level, in my opinion, has not for objective to replace completely the high level in a sense. This idea starts with the general idea of I was thinking of how we are learning to drive a car. So when we try to learn to drive a car when we were younger, we think, okay, I want to go outside the parking lot, and then you use your inside LLM, your thoughts, to say, yes, I have to turn the key, push on the clutch, turn the wheel, look around. And then your sensory motor parts try to do what you are thinking about, so turning the keys, everything like that. And when you go outside the parking lot, you kind of stitch everything together to learn these abilities. Okay, and similarly, you are able to compile this trajectory into going outside the parking lot, and after some time of training, you are just thinking, okay, I want to go to the roundabout and I have to go first out of the parking lot, and then your sensory motor part acts. But at no point you are thinking, yeah, I have to do 500 kilometers from Paris to the middle of France, and then you go out of nowhere. So there is always a balance, and there is a point where you don't want to let the low level play for like thousands of steps. And perhaps if you have very complex goal like, this goal like collect call, you are not at perhaps in this setting you can learn from a low level to collect call, but perhaps it's not useful. Perhaps the first thing you just have to be able to learn place table and then collect call. You will always have to break at some level the difficulty of and just to get something manageable. And indeed, if you imagine that you will reach very, very complex goal space, but even as human, we are not just asking a sensory motor system to just do all the work for us. We have just this kind of subroutine that we have, and we call when we need them. So I think there is always a balance, but there is no need for thinking, yeah, I want to compile everything in my lower level.
Yeah. So generally, the one thing that your work naturally inspires is to make the low level, in fact, more efficient. And that's what we do as soon as we invent all these shortcuts, right?
Yeah.
To do things, we invent new technologies that we invent new GPUs that are faster or whatever. And environments that contain that affordance would be really, really powerful.
Yes. In a sense, we can say we can add to Heracles the possibility to use tools. So at some points, this subroutines is delegated to a tool. Yeah. So yes, that would be great.
Very naturally. But, okay. Well, penultimate question, just to touch on world LLM. So, I think this is really cool work. I believe that natural language explanations should be really important. I was sad that it didn't work as a slam dunk.
Yes, we hope so. We tested that for, I think it was like 6 months when we tried to do that, and just at the end that was kind of beginning to work. But it seems simple when we expose the things like that, but there is a difficult balance between how much you revise theory, how much you want to test them, how you push the agent to explore the environment. And I think we're just scratching the surface, and we want to go deeper in future works on it. But yeah, I think it's, in a sense, it's already amazing that we can generate some rules and that push the exploration, so that give a lot of hope for the future. Yes, at some point we are like, oh yes, it's not working that much, but at the end we are very hopeful about this situation. We say, yeah, now we're beginning to understand it, because there is no other attempt like that.
So if I understand that response correctly, your kind of reason for why it was difficult to get it to work is the interaction between tuning the interaction multi-agent system. Yeah, that's really fascinating. I'll come back then to a last sort of synoptic question, which is coming back, I think, to your first or second slide.
Okay.
Where you kind of introduced this autotilic approach to open-endedness. Yes, exactly this one. So this is a way of achieving open-endedness via an RL paradigm, really. If I were to sort of ask a sharp question, I'd say, well, open-ended systems don't have explicit goals at all, like natural evolution is an example. So what's gained and what's lost by framing open-endedness as iterative goal construction and goal satisfaction in this way?
Yeah, so I think the easy part is saying what we can gain here. So we are obviously using like a goal space, and we're framing that with goal because it has gained some framework to work on. Usually when we think of the goal space, you say, yeah, I can decompose a goal into sub-goals, for instance, or there is related goals and I can do some generalization. And that's the thing we've explored and exploited inside, for instance, Magellan. Because we have a goal space, okay, yeah, we have one goal, you can explore and try to generalize to other goals. If we are more in open-ended evolution, for instance, of the agent like natural evolution, we are losing this kind of goal space more like in an energy kind of way, where we try to minimize arrive to a point of minimum energy depending on the system, and it's moving. It's way more complicated to do so, and I'm not completely sure. I'm not completely sure that language is that easy to apply to such a goal space. We can still use it to describe some environment and reuse it. For instance, there is as I told before, this work from the team, expedition and expansion, that use it on a continuous cellular automata, and you use VLM to do some description. So you can still try to put some structure on this complex settings. The idea is like in form you use language to do some classification and generalization, as I explained there. Sorry. So if you are using language here, you are doing some categorization and generalization. So even if in place where you don't have goals, you can say, okay, this part of the space I'm calling like that, and I'm trying to be in this direction, because there is no like, you cannot pinpoint a goal in like a cellular automata, but you can kind of define some parts, and you need some structures at some point. You need to build some structures to exploit it. So it's less making a hypothesis here than to impose a structure framework. So perhaps you lose a bit, but you win so much with the structure that I think it's still worth it.
Great, thank you.
Okay, so I have two questions, and then I think we'll have some comments from your advisors. Two quick questions, and maybe I shouldn't say naive, but it's not my field. You have these rules for your environments, right? Around their behavior, and from my understanding, some of them are unspecified, and some of them you hope to discover in the course of. How do you make sure they are consistent?
When you want
because if they are not, possibility and all that.
So usually we are using like simple environment where you just few rules inside them, and yes, I think we are hoping that the rule. We are not hoping that rules are consistent. I think no learning can truly happen in like an environment with inconsistent rule. Like you cannot generalize from them. So
do you check that?
we are just using usually some RL environment that has already this kind of property. We do not check, we do not verify that the environment that is always used kind of have this property. But indeed, it's if you build an environment, for instance, I think if we're thinking about Magellan, where we build the environment here, it was something that we have to check that all the combination obey to strict and regular rules, and that's why we also use this kind of simple combination of elements, and we do not push further with a lot of categories, because it's usually that can bring some errors, and these inconsistencies will kind of break down the system because you cannot generalize anymore. So it's better to have this simple environment. And we hope if you apply that to our current environment in which we live in, we are living in something in an environment with that is consistent, and we hope at least it's our hypothesis, work hypothesis. But yeah.
How do I know? But the environment we live in, we don't have precise rules that describe it in a consistent way. So
Yeah.
In physics. So.
Yeah.
Okay. The other thing is that, by the way, I should have said, it's a very nice presentation for working on this work. But from somebody outside the community, those are very, very toyish problems. And these toyish problems are, of course, well adapted to LLMs because they are very discrete. As far as I understand, at least very discrete set of states, and with a simple structure. If you want to move to something closer to the real world, discretizing your state space in a reasonable way is by itself a very hard problem. So, do you have any thoughts about that?
Yes, that's true. So in GLAM, for instance, we have this description of the environment that is easy to do with vocabulary because it's like a 2D mini grid. So we can do so. And one of the limits of such an environment is, as you tell, this discretization, and that they are fairly simple. And it's difficult with language, for instance, to imagine caption for like complex 3D words. And we could replace such a LLM with only linguistic inputs with a VLM, which share linguistic and visual inputs, and we replace the linguistic input with the visual inputs. For instance, directly using an image and a goal specified with language.
Yeah, but in that case, I'm not specialist of VLMs either, but the VLM does most of the heavy lifting, right? And the discrete nature comes against some VLMs. If you are in the visual domain, discretizing the visual domain is very hard. You don't know how to do that.
I think I did some attempts of using a VLM, for instance, on Crafter. It was a failed attempt, to be honest, to say, okay, it's already kind of complex to describe that with language. I will directly try the VLM and just take the goal expressed with language and use this image. And after I tried that for 4 months, and that failed. And one of the key thing I get from that is VLM. Now I kind of train to use image to do some captioning. Like they just learn to, okay, I have an image, but they don't know how to do some reasoning. And so they are less prominent than their LLM counterpart to do so. So here I still replace, because it's still manageable in this environment, to replace the image by a caption, even widely imperfect caption. But that's a true problem in general. You need to go through some kind of discretization. Still, you can manage to use that for like kind of complex environment. For instance, you can imagine an LLM that do some code and that interact through an API with different tools. And even if it's not like our continuous daily life environment that is complex, there is still fairly complex environment that you can go through with text.
Sure. Everything that textual the code.
Yeah. So yes, that's true. It can look like a toyish problem, but there are some papers that have adapted GLAM to other techniques, and especially that like PhD that I told later that use this kind of constraint decoding, and they did test on codes, on code generation, and you could imagine also doing some tool use with that. So even if it's perhaps not the most adapted for like our visual continuous environment of that we experience, it's still interesting for a lot of environments.
It's not just visual. You can imagine a robot that has moved.
Or like ultrasounds.
Okay, you have answered already 5 million questions, so it's not that let your advisors not ask questions properly.
Olivier, do you want to go?
Okay, sorry, I couldn't hear Jean very well. Yeah, so just a word to say that we are 3 people in the supervision team. So I won't speak too much about the collaboration with Thomas to let the other 2 say things. I just want to say that I was very happy to be part of this supervision team, okay? And I want to thank Thomas because his work has led us to a lot of progress in our approach to autotailing agents and to LLMs and a better understanding of what LLMs can do and cannot do. Maybe, if I may, I will anyways ask a very open question to Thomas to see how he reacts. So one point with autotelic agent is that they decide on their own goals. So they may decide to go fishing and learn how to fish, okay? But we are also interested in having agents that are interesting to humans and that are useful to humans. So what would you add to what you did so far so as to have autotelic agents endowed with language capabilities that are more useful to users?
So yes, thank you, Olivier, for this great question. And yeah, indeed, we want like to have this open-ended agents to explore the world, but perhaps not in an unconstrained way. For instance, if we're in a mathematics environment, it would be great to put an open-ended agent that generates some new theorem and do some new discoveries. But for some mathematician, perhaps they would like to be constrained in direction of one specific goal, perhaps solving the Riemann conjecture. Like they are mostly interested in that, and they don't want the agent to go in completely different directions, still interesting, but completely different. And one of the idea that we could add is like, for instance, in Magellan, one of the possible ideas is because you have at the end of the training or at some point in the training, you get a sufficiently good embedding of the goal space where the goals are kind of structured. You can place one of the goals you want to reach as a human. You know already what kind of goal you want to reach. And you try to sample goals that go inside this direction. You could say, okay, I want to sample goals alongside the geodesic inside this environment to find the succession of goals that are the most interesting to get there. For instance, I want to build a castle in Minecraft. Perhaps at some point, learning to fish, to do some to go fishing is not very much interesting. But if I between inside this goal space, between the goal I mastered that is building a house and another part of the goal space that is building a castle, I can sample directly inside the embedding space some interesting goals that are both close semantically, but also that are interesting in terms of competence. So that would be an interesting way to do so. But indeed, like this kind of semi-constrained paradigm where we want both a high level of exploration because we don't know how to solve the problem, and at the same time being able to like kind of direct it a bit this exploration to avoid like inside when we are like in the big complex environment of our world, to avoid like going in not interesting direction for humans at the end. That's a very interesting direction that I also would love to explore. How we can decompose goals that we don't even know how to do into goals that are still difficult and we still don't know how to do, but seems like more manageable. Interesting direction indeed.
Okay, thank you, Thomas. I won't ask more questions because we don't have much time. Yes, thank you.
Thank you.
Yeah, I just wanted to say congratulations on the impressive work you did these last few years, Thomas. Your subject was clearly not an easy one. You had to look, in a sense, at the two sides of the same coin, what RL can bring to LLMs to connect the language to sensory motor environments. And on the other side, what also can LLM bring for dealing with open-ended error, and how to exploit the the common sense that the LLM embed, and you did it very nicely. Also a difficult problem in an highly competitive domain with a lot of teams on it. Also, grounding comes now as something that is kind of evidence for going to general artificial intelligence. And yeah, you have the chance to be one of the first to propose things like that. And yeah, congratulations, because you succeeded to keep some kind of advance in that domain for all these 3 years. And it was very easy.
Thank you.
And it was not easy also because you had to manage with 3 very different points of view a lot of time. And we had very rich discussions at each of our meetings. In fact, that's, yeah, it was fully remote for me, this situation. We meet each other in person for the first time today. But in the same time, I feel that you were a very close teammate to me. And that's because you are very dynamic and you always come with many new things, new ideas, new works to discuss with us. And it was a very good opportunity for me to work with you all. And thanks. I also wanted to thank Pierre-Yves Olivier for having invited me in that team. That brought a lot to me. Very things that I have in mind now that I have done before. And yeah, thanks also for the collaboration with various members of from Flowers. We had very rich collaboration. And yes, thank you for everything. Congratulations. Have a nice time now.
Thank you very much. So just before talking about you, Thomas, I would like to thank very much all the members of the jury for being there with us today. All of you have been doing extraordinary work that have inspired members of the team. And so that's so great to see the scientific discussion and the question you asked, which allow us to see different perspectives on what we aim to do. Thank you also very much, Olivier and Sylvain, for the great collaboration. It's always super stimulating to have these complementary perspectives. I hope we get the opportunity to collaborate in a similar setting in the future. And also, thank you to the whole team, and in particular, people who have been collaborating to some of those projects. So as you can see, that we work a lot collaboratively. In particular, thanks to Clément and Loris, because I think that the 3 of you have been forming kind of a dream team for several projects, and it's been really great and pleasurable and still intellectually stimulating to work with that dream team on those projects. Thanks also to other people like Guillaume Pourcel, Salim Aïssi, or Guillaume Lévy, who contributed very strongly in some of the dimensions. And all of this is actually very reflective of something that's amazing with you, Thomas, is that you're a great team player. And you're a great team player for several reasons. First of all, you're extremely creative. You are bold, like not being afraid to go for ambitious goals and solving difficult challenges, and always positive, trying to push forward the obstacles, to handle them, and leading everyone to push forward everything. And I have to say that beyond the scientific achievement you made during your PhD, your skills also were illustrated by an absolutely amazing achievement, which no one else in the history of the team has been able to do, which is achieving to do all the administrative steps at the University of Bordeaux to get the official authorization to do an internship in a company for a few months. And this seems to be like nothing difficult, but anyone who knows University of Bordeaux, it is an extraordinary achievement. But no, I mean, really, I mean, that was amazingly cool to work with you, and also because you have a lot of humility. Please keep that humility with you. The combination of humility, creativity, and boldness, that's really great. The capacity to listen and to iterate on the work. The presentation today is the result of iteration of many rehearsals, and you can see that on the different projects. And I learned so much from you, and not only on the scientific project. I mean, just remembering all the discussion we had, for example, over lunch, where Thomas has been telling us amazing things about history, about geography, about exploration project. He's been doing in remote places of the world. Some of you don't know, but Thomas is an explorer, not only a scientific explorer, but also a real explorer, you know, with the backpack. And, so thank you very much, Thomas, for all of this. And I'm really curious to see what's next.
Thank you very much. Thank you very much.
Okay, so I think at this stage, we leave. We stay here, everybody leaves.
Yes.
Just turn.
The jury deliberates in the room. And so on the Zoom,